Welcome back, class. Today we will review the topic of exponents and some of the properties of exponentiation. We will then dive into PEMDAS and look at how one can perform more complicated sequences of calculations in these more fancy expressions that you might be given in this particular class. A lot of students who take this course are going to remember the basic definition of exponentiation. Whenever you exponentiate a number, such as the variable a shown here on the left, all it means for you to do is to take that number and multiply it by itself that many times. Now, the tricky part of this is to remember that a could represent any number that you want it to be. A could be a whole number, it could be a negative number, and it could be a fraction. But regardless of the number that you might be presented with, when you exponentiate that number, it means that you're going to take it and multiply it with itself. Now, conceptually, one can think of exponentiation as being an extension on multiplication in the same way that multiplication extends addition. Remember that when you say 2 times 3, what you're really asking for is you're asking for someone to find the total of 2 sets of 3. And so what that means for you to do is it means that you need to add 3 with itself 2 times. 3 plus 3 gives you 6, and so 2 times 3 is the same thing as 6. Well, exponentiation is the same way just for multiplication. It asks the question, well, if you're multiplying a number by itself a certain number of times, what is that equal to? Okay, listed down on the bottom of the page, I've got a couple of examples of exponentiation. Now, with exponentiation, as I said earlier, we can take any number and raise it to some power. And all that means is that we're going to multiply the number with itself that many times. So if I take the number 5 and exponentiate it by 4, it just means we'll multiply 5 with itself 4 times. So you'll have 5 times 5 times 5 times 5. A student might be asked in this class to evaluate such an expression, i.e., perform this calculation. If they were asked to perform this calculation, the student just has to remember the associative law. The associative law says that you can perform the multiplication operations in any order. So a student could start, say, on the left-hand side reading right and begin evaluating this expression by first performing the multiplication of 5 and 5. On the other hand, you might see teachers in other classes start on the right-hand side, reading left, and they might perform the multiplication of the last two fives. Still, yet, you might as well have started in the middle because the associative law says it doesn't matter where you start because all of these numbers are multiplied together. It is an associative law case. We can multiply the numbers in any order. We choose the order. So, but for the sake of simplicity, I usually start on the left and move right just because that's the way we read a book. So I'm going to take these first fives and we would multiply them together to say get the number 25. And then what you're going to do, class, is you're going to need to rewrite the quantity that's remaining in the next line. Now I'm writing going up because, I'm a little bit cramped for space, but the students need to write this quantity usually below where they're working. So in the line directly below wherever you've written out your problem statement in order to obtain full credit for their answers. You then do the process of multiplying 25 and 5. So 25 times 5 is going to give you 125. If you can remember that 5 quarters is $1.25. On the other hand, if we didn't remember that 5 quarters is $1.25, we could have always, written out the multiplication algorithm and have done 5 times 5 gives you 25. Carry the 2. 5 times 2 is 10. 10 plus 2 gives you 125. We now have to perform the multiplication of 125 and 5. 5 times 5 gives you 25. Carry the 2. 5 times 2 is 10. 10 plus 2 is 12. Carry the 1. 5 times 1 is 5. 5 plus 1 gives you 6. So our answer is 625 if we were to evaluate this expression. Now note that many times in this class, what we're going to be doing is we're going to be actually going from a complicated expression, such as 5 times 5 times 5 times 5, and we're going to reducing it. We're going to be simplifying it to something that is more basic looking, such as 5 raised to the fourth power. I'm rarely going to ask you to actually evaluate an exponential form because exponents have a way of getting out of hand. I mean, 5 is not a particularly large number. 4 is not a particularly large number. And yet, when we took 5 and exponentiated it by 4, here we are with this ridiculous number 625, right? So, very rarely, because it's so tedious to perform these calculations by hand, and all of the calculations in this course are required to be done by hand, very rarely am I actually going to ask you to evaluate an exponent. But you should be confident enough to do it if you were asked to do so. All right. You could have also exponentiated a negative number, such as taking -8, raising it to the third power. And what's going to confuse a lot of students, or what a lot of students are going to forget, is that when you exponentiate a negative, you don't just slap a negative outside in the front of your value or in the front of your answer. Instead, you have to carry that negative and keep multiplying the number by itself that many times. So in this case, you wouldn't say just slap a negative out in front. Instead, you'd have to do -8 times -8 times -8. And so the second tricky part is that, well, now you actually have to perform multiplication with negative numbers. And if you remember, a negative and a negative is a positive, but a positive and a negative is going to be a negative. You have to remember those rules. So you'd have a negative and a negative. That would be a positive. You then do 8 times 8, which is 64. And I'd have to bring down my -8 and do 64 times -8. Now, going over to the side of our page, we can do just that. 8 times 4 is, well, 8, 16, 24, 32, right? So you're going to drop a 2, carry a 3. Now, what we're going to do is we're going to need to do 8 times 6, which is 48, and add 3 to 48. So 48 plus 3 should give us 51. So our answer should be uh, not 512, though, because you've got a positive and a negative, but negative 512, right? So just go ahead and check this, and I did indeed do my multiplication correctly. So you will, in fact, have negative 512 as your answer. More tricky yet, you could have, say, a fraction such as 4/5, raise it to an exponent such as 5. And that means that you're going to have to multiply the fraction, the whole fraction, with itself that many times. Now, what's confusing about, say, exponentiating a negative number or exponentiating a fraction is that psychologically, at the lower level classes, we're used to looking at a negative number and thinking, look, that negative sign is a subtraction symbol. I'm taking away some value. And while it's true that the operation that results in a negative is in fact a sequence of subtractions, right? That's not what the negative number itself represents. In fact, the negative number is its own type of number. And the same is true with fractions. When you've got a fraction, such as 4/5, it's not merely 4 divided by 5, right? Although that's true. Yes, in fact, it is 4 divided by 5. Additionally, it's not simply like you're taking a candy bar, cutting it up into 5 pieces, taking 4 of that. Instead, you really need to mature in your thinking process and start thinking about these fractions as being their own number. As a consequence of this, because it's its own number, when you take 4/5 and raise it to the power of 5, it means you've got to multiply 4/5 by itself 5 times. All right. Now, an interesting result, however, of taking a negative number and raising it to a power is that whenever you raise a negative number to an even power, you're going to get a positive version of that number. If you raise a negative number to a odd power, you're going to get a negative version of that number. So even without actually performing the multiplication operations, and if you just remembered this particular rule, which I call the positive and negative exponent rule, If you just remember this positive and negative exponent rule, you're going to help yourself out on the homework, okay? Because the homework problems do have some of this. So, just as an example of how this rule can help you, say you took -8 and you raised it to the third power. If you knew that -8 raised to the third power, because the exponent itself is odd, you just need to slap a negative sign out in front and do the multiplication of 8, or sorry, do the operation of 8 raised to the third power. So if you did that, you would have a negative sign out in front, and you would just have to calculate 8 times 8 times 8. Okay. The reason for this is because of how when you multiply a negative and negative, you get a positive. But when you multiply a positive and a negative, you get a negative. So if you have an odd number of terms, you will always have a negative sign that's floating out in space. And so once you've performed your multiplication operations, you'll have a positive quantity multiplied with this remaining negative term. And that will then result in a negative. So just as an example, if you have -8 raised to the third, we know that's -8 times -8 times a -8. You would naturally, starting on the left, reading right, take -8 and multiply it with the second term, which is another -8. Without doing the multiplication, just looking at the negative symbols, negative is a positive, so that gives you a positive here. And you would have a negative term, the remaining -8 that you would then have to multiply with. Well, a positive and negative gives you a negative. So here again, we didn't actually have to keep bringing down these negative symbols. If we can just remember this rule, we can, in fact, perform the multiplication operations separate from accounting for the negative sign. Another example would be -8 raised to the fourth. Now, because my term that I'm raising -8 to is even, we are going to have an even number of negative numbers multiplied with each other. And that means that because a negative and negative is a positive, if you look at the first two terms, negative is a positive. If you look at the last two terms, negative is a positive. So now you'll eventually have two positive numbers multiplied with each other, and that will, in fact, result in a positive. Now, remember, while I am forcing the direction that I read this particular problem and perform the multiplication operations, because of the associative law, you could have started anywhere. And if you're taking a negative term and you're raising it to an even value, regardless of where you start in that expression and begin performing that multiplication process, you are going to ultimately result in a positive answer at the end of the day. And so in this case, we would have just had a positive 8 raised to the fourth. So we would just need to do 8 times 8 times 8 times 8. In this third example, I have -8 raised to the fifth. And to just show you, just demonstrate one last time that this addition and subtraction exponent property is extremely useful. If you had just looked at this problem statement, you would have a -8 multiplied by itself 5 times. And the first two -8s would, of course, because you've got a negative and a negative, that would give you a positive. The second set of -8s would be a -8 times a negative, and that would again give you a positive. But then you would be left with this trailing -8 hanging out in space. And so, because you got a positive and positive, and that would give you a positive, eventually you would have a positive and a negative multiplied together, and that would result in a negative. So just remember this rule, and you don't have to do all of the accounting for the negative signs. You can just, you know, perform the calculation of multiplying the 8 by itself 5 times and slap a negative sign out in front. Moving on to PEMDAS, there are many instances in this course where you're going to be asked to take a very complicated looking expression, such as the one shown on the right, and actually evaluate, determine what this expression is equal to. Now, it turns out that in order to do this and obtain a correct answer, you're going to need to follow a special set of rules called PEMDAS. And what PEMDAS stands for, if you guys recall, is parentheses. That's what the P means. exponents, multiplication, division, addition, and subtraction. So for us, what that means to us is that we're going to look at this expression, and wherever you see parentheses, we're going to evaluate, we're going to calculate whatever happens to be in those set of parentheses first. And not just a set of parentheses, but what is inside of the innermost set of parentheses first. So in this case, we have one set of parentheses that you see here. And PEMDAS is going to tell us that we need to perform the 5 minus 4, which gives us 1. Okay. Now you would have 8 minus 7 times 1 plus 2. PEMDAS would then insist that we need to perform the multiplication operation, the 7 times 1, which gives you 7. Now is where the tricky part begins. It turns out that it doesn't matter if you do addition first or subtraction first. It really doesn't matter because there's actually an equivalence between addition and subtraction. Really, subtraction is just adding a negative number. Okay. So, what that means to you is you could do 8 minus 7 if you prefer. That would give you 1. And then you could do 1 plus 2, which would give you 3. However you choose to work through one of these expressions, I need to see on your homework paper every single step that you've written out, okay? In order for you to receive a full credit for that particular assignment. If I don't see all of the steps written out, if you just like say, give me 3 and circle it or something, that's going to be no credit. Okay. I need to see every single step worked out correctly from the top to the bottom. All right. Now, what's tricky about PEMDAS is a lot of students like to read from left to right. I mean, I like to read from left to right. And the issue here is that they might start with saying, hey, there's this operation starting on the left, going to the right, 8 minus 7. So that would give them 1. So then they would have 1 times the quantity 5 minus 4. So now maybe they do 5 minus 4, which gives them 1. And they would be left with 1 times 1, which is 1, plus 2, which gives them 3. And the confusing part is we happen to come up with the same answer starting on the left going right and using PEMDAS. And so what gives? Why are we doing PEMDAS if it's possible, if there's the potential for obtaining the same result? And the answer to this question, the reason that we use PEMDAS is going to minimize the amount of error that we have in our calculation. As you're performing calculations, different operations introduce different levels of error. When you did exponentiation, such as this 5 raised to the 4, because you can take even small numbers and exponentiate them with other small numbers, such as 5 raised to the 4, and that gives you some ridiculous value at the end of the day, such as 625. It means that the amount of error, if you were to do that incorrectly, is much, much greater with an exponent, whenever there's an exponent present. So exponents have what is known as a high level of precedence because they introduce a lot of error into your calculation. Now, the reason why an exponent is below the parentheses is that the parentheses stand as a social convention that tells you do this operation first. That's literally the job of a parentheses in mathematics. It says you have to do this operation first. Not only that, but the parentheses also tells the mathematician that you're dealing with a whole quantity. What does that mean? That means if you're dealing with a number 10, this is just a number floating out in space. But I hope everybody would agree that 10 is the same thing as 5 plus 5. If I wanted to illustrate to someone on paper that, you've got 10 of something, but maybe it's broken into individual units, such as 5 and 5. What does 5 represent? Well, maybe it represents little balls. So you've got 5 balls here and 5 balls there. Yes, there are, in fact, 10 balls total, but what I've done is I've illustrated the arrangement of the balls using the sequence of parentheses, okay? And similarly, the sequence of parentheses also tells the mathematician that, hey, you need to do this operation first. All right, so exponents comes below parentheses because the parentheses is going to tell everybody what we need to start with. But then after exponents, you've got multiplication and division. So what's going on here? Well, a multiplication operation, as it turns out, is going to introduce a lot more error than just simple addition. To think about this, you might consider, say, 625 plus 5. If we were to add, say, 5 with 625, we would get 630. But if we were to take 625 and maybe we were multiplying instead of adding, well, there's going to be a lot more error that is introduced from a multiplication operation. So 5 times 5, that gives you 25. Of course, you would have to carry the 2. 5 times 2 is 10. 10 plus 2 gives you 12. Carry the 1. 5 times 6 is 30. 30 plus 1 gives you 31. So if you were doing multiplication instead of addition, or if you accidentally thought that you needed to do addition instead of multiplication, you're really, really off the mark, okay, with 3,125 instead of 630 or vice versa. So, just as a matter of social convention, we're going to say that multiplication, because it introduces the next level of error, must come after exponents. Doesn't introduce as much error as exponents, but it introduces much more error than addition or subtraction. Now, multiplication and division have the same level of precedence. So you can perform multiplication and division in any order that you choose. Um, because division is just multiplying with an inverse. We'll look at that. I believe it's next chapter. We'll look at that a little bit. Okay, let's look at some problems from the textbook. Okay, so this is problem 91 from the textbook. And problem 91 gives you this wonkadoodle formula, and it's asking you to evaluate the expression. What are you going to do? There's so many different operators. You've got this massive looking fraction. Oh my goodness. Well, we're going to take a deep breath, right? Because a lot of students, their blood pressure starts to rise the moment that they write down the math. And so we need to calm ourselves down. But then basically, the only thing that you got to remember is that whenever you're evaluating one of these expressions that has a fraction, it's like there's an invisible set of parentheses that is in your numerator and in your denominator. So students shouldn't panic about, do I need to start on the top? Do I need to start on the bottom? Da 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 da. Da. You could start wherever you choose, okay? As long as you follow the rules of PEMDAS. My recommendation to students is that for these problems, just rewrite PEMDAS somewhere on the side of your paper so that you remember what operation you need to do next. Now, I'm going to start on the bottom since it looks like a less complicated problem down there. And because I don't see any exponents, I'm going to look and we could do multiplication. There is a multiplication operation. I've got 16 times 2. And I also have 4 times 0. So let's go ahead and we'll do those operations. So I'm going to rewrite everything that you see above. I need to see this on your paper, guys. You got to rewrite it. And for each operation, rewrite your problem statement. So if you chose to do 4 times 0, then just write the quantity and then rewrite everything else. If you chose to go with 16 times 2, write that quantity and then rewrite everything else. Now, 16 times 2 is going to give me 32. So all I'm going to do is write 32 minus 4 times 0. 4 times 0 is 0. So on the next line, I will write 32 minus 0 in the denominator, and I'll have 12 minus 16 divided by 4 plus negative 24 in my numerator. 32 minus 0 is 32. You've got 12 minus 16 divided by 4 plus negative 24 on top. 16 divided by 4 comes next. Why? Because we would then shift to looking at the quantities in our numerator. Because we've got nothing going on in our denominator, we're basically finished with the bottom. We can just shift our attention to the numerator, to the top of our fraction. And as we're scanning through the top of our fraction, you'll note that the only thing really going on the top is that you've got a division operation. Okay, you've got some addition and some subtraction operations, but the big one is going to be division. So let's go ahead and we're going to attack that first. 16 divided by 4 gives you 4. So now we will rewrite 12 minus 4 plus negative 24. Another good habit to do whenever you're analyzing these PEMDAS style problems is to just check through your equation. And if you see a positive and a negative symbol, go ahead and feel free to switch that to a negative. It's a good habit. Okay, so now we just have a sequence of subtraction operations. I'm going to start on the left going right. I'll just do 12 minus 4. So 12 minus 4 gives me 8. I'll then have 8 minus 24 all over 32. 8 minus 24, let's see, that should be 16, negative 16. And this will be all over 32. Positive and negative is a negative. 16 does indeed divide 32. 16 goes into 32 two times. So you would have a 2 on bottom. So you'd have a negative 1/2 on top. So what did I do? I took negative 16. And I said, if I divide this by 16, I'm going to get 1 on top. And if I take the 32 that's in my denominator and I divide that by 16, I get 2. So that's where I got this negative 1/2. Let's try another problem. This is going to be problem 94 in your textbook. All right. And let's just go ahead and we'll write out our PEMDAS somewhere to the side. Now, the tricky thing about PEMDAS is that this particular problem is written in such a way as to confuse us because, yes, there are parentheses, but what students' eyes are going to go to is they're going to go to trying to attack this whole thing inside of the sequence of parentheses, right? And of course, they don't see that there's anything that can be done. And so then they'll move on to exponents. And then they say, well, how can I attack this with exponents? If you think about it, 9 times 2 minus negative 2 cubed all over blah, blah, blah. They're going to try to do this multiplication twice. And of course, while that is correct, it would not necessarily help them obtain the correct answer. So there are better and there are worse ways of trying to approach these problem types. In my opinion, what you should do instead is look to see if in your numerator or denominator there's anything that can be simplified. Okay? Because what you're dealing with here is, yes, you're dealing with a fraction, but it's also as though in your numerator of the fraction, there's this secret set of parentheses. And in the denominator of the fraction, there's this other secret set of the parentheses. And so when we're really talking about PEMDAS, we're saying the innermost set of parentheses, that's what we're referring to, needs to be evaluated first. So consequently, you could actually look at the numerator and we could try to clean the numerator up, or we could look at the denominator and try to clean up the denominator. Now, I think probably the denominator here again would perhaps be easier to simplify. So I'm going to start there. 4 squared gives me 16. So I'm just going to write everything else all over again. This is a good practice in accounting because it keeps you, it forces you to write everything over and over again. All right, so let's look at this denominator again. We've got 16 plus 3 times -1 raised to the 5th power. I don't see anything apart from that exponent that's going to cause us some trouble. So let's go ahead and we'll do -1 raised to the 5th power. Now, if you remember your negative exponent rule, because we are taking the -1 and we're raising it to the 5th power, we know that that's just going to be 1 raised to the 5th. And 1 to the 5th is going to just be 1. Yes, it will in fact be 1 times 1 times 1 times 1 times 1, but whenever you multiply this sequence of ones together, you're just going to get a -1. So in my denominator, I will write -1 times 3 plus 16. And in my numerator, I will write 9 times 2 times minus a -2 raised to the 3rd power. All right, now we have to repeat this process 3 times -1. That's going to give me a -3. Because we have a positive and a negative, that's going to be a negative. And in my numerator, nothing changes. Try not to write sloppy like I'm writing. Try to keep all of your numbers as nice and pretty looking as possible because it's going to result in most likely less problems, less issues. All right, 16 plus a -3 is going to be the same thing as 16 minus 3. So you will have 9 times 2 minus -2 cubed on top, and then 16 minus 3 on bottom. And that entire thing's raised to the 2nd power. 16 minus 3 is going to be 13. So you'll have 13 on bottom, 9 times 2 minus -2 cubed on top. That quantity will be squared. Let's look at now the innermost set of parentheses here, and specifically the exponent operation, because I don't see anything else that we could really do. I mean, I guess we could actually probably attack this multiplication if we wanted to, because that won't really change the answer. But just for the sake of doing things consistently, let's go ahead and we're going to attack this numerator, and specifically we'll look at -2 quantity cubed. Again, because of the negative exponent rule, we're taking -2 and we're raising it to the 3rd power. 3 is an odd number, so you can just slap a negative out in front and you'd have 2 times 2 times 2. 2 times 2 is 4, times 2 gives you 8, so you will have a -8. Now, the tricky part is it is being subtracted from 9 times 2. So you got to remember it's being subtracted from 9 times 2. Because it's being subtracted from 9 times 2, we can go ahead and flip that sign. Let's go ahead. We're going to do 9 times 2 plus 8. Well, 9 times 2 is 18. So we'll now have 18 plus 8. 18 plus 8 gives us 26. 26 divided by 13, that's going to be 2. So 2 squared, that is going to be 2 times 2, which gives us the answer of 4. And voila, you have your solution. Pretty much all of the problems are going to require you to go through a similar set of procedures that we will see and practice with in class. But for now, I think we will leave it at that. And if you guys have any questions, feel free to send me an email. My email address listed in our syllabus. But for now, I think we'll call it a day. So good luck to students on their homework, and I will see you later. Bye-bye.